Okay, so shall we start? I'm Subhro from University of Tokyo. So I'm chairing this morning session. The first talk this morning is a tutorial lecture given by Professor Subhro Bhattacharjee of the International Center for Theoretical Science, Bangalore. He received his PhD in 2010 from Indian Institute of Science, Bangalore. And after completing his PhD, he worked as postdoc at the University of Toronto, McMaster University, and the Max Planck Institute for complex systems. Since 2015, he has been a faculty member of International Science for Theoretical Science, Bangalore, and now he's an associate professor. He's actively working on a variety of quantum computing programs, including the frustrated magnetic, geometry, political pages, and also magic decay. Today, he's going to give a tutorial lecture on modern basis.
Thank you. Okay, so I hope I'm audible both to people here and online. Just feel free to stop me at any point. I'll basically try to build upon various things that have been discussed, particularly things that Arun have been discussing in the last 2 days. So the plan is as follows. I'll set up the problem roughly by the middle of this talk. And so I'll basically set up the problem of how to
Right. So that's the. It would be.
Yeah, I'm just saying that if it is big enough. So how to think about quantum spin liquids in quantum spin liquids, and then I'll delve into an example. And finally, how to generalize general theory for SL, mean field plus fluctuations. Okay. So this is what I want to cover. Is this visible to everyone in this room? Okay, so roughly I'll basically try to end here in the first talk and then take this general structure up in the talk after lunch. Okay, so of course, some of the things that I'll say, particularly to start with, would have overlaps with other talks, but hopefully the overlaps would be minimal, and maybe it would help me set up some of my notations and thought process. So the first question that I'll start with is, and quickly point out that how do we think about many body systems? And there are various ways to start. The one convenient way to start is to point out that there are 3 basic ingredients. We need to say what the degrees of freedom are. Then we need to say what the symmetries of the problems are. And then the Hamiltonian. So these are the 3 ingredients that when we are faced with the when you got a problem, this is what we want to point out to formulate the problem. Okay, and I'll specify some of the features of these 3 things that would help us to think about spin liquids and contrast it with things that we are somewhat more used to, the symmetry broken phases. Okay, so the first aspect, which is this degree of freedom, is that the Hilbert space that so these degrees of freedom for quantum body systems are typically electrons, spins, or various cold atom bosons, etc. So, but there are many in number, typically 10 to the power 23. That's the number of degrees of freedom. And what in a quantum system, we are basically dealing with this many-body Hilbert space. Okay, but this Hilbert space has this very nice structure, which I think it's very important to appreciate, that the total Hilbert space breaks up into a tensor product of local Hilbert spaces. Okay, and this is a very important feature to characterize many of the unconventional things, particularly things like entanglement, etc. You need this structure to make some of the calculations very well defined. Okay. For example, if one thinks about degrees of freedom to be a set of spins, spin halves, then at every site, I'll keep on drawing lattices of various kinds. Say on a square lattice, if I have spins at every site, then this local Hilbert space basically consists of, at every site, say site I, two states, up and down. Okay, and at every site there is such a two-dimensional Hilbert space. Okay. Generally, the dimension may change if instead of taking spin half, we take spin 1. Then I have 3 sides. So we have some qubit. Okay, in the sense that q-dimensional Hilbert space at every point in space. Okay. If I have an electron, then the Hilbert space has 4 states: 0, no electron, 2 electrons, 1 up, either in up or down. So that corresponds to q equal to 4. Okay. So this is one feature of the problem which is very important. What it means is that at every site, if there are q states, I can write q squared minus 1 on-site operators. Okay, so for spin half, there are 3 operators which are Sx, Sy, and Sc. Okay, and for electrons, one can write down 4 squared minus 1, 15 operators. Okay, on-site operators. So this is the structure of the local physics, on-site physics. And then if we know the on-site operators, so say O of I, okay, then we can form many-body operators by just taking tensor product of operators. Okay, so we call it O, I, A, L. So these kinds of operators. If we take 2 spins, we can take the spin composition of spin operators, and then we can try to find different representations of these operators, somewhat like using the generalization of Clebsch-Gordon decomposition, etc. Okay, so these becomes very useful. The structure becomes very useful once we want to understand the various symmetries, etc., how they act on the degrees of freedom. Okay, and this, as you would see, hopefully, that we of course use this to understand ferromagnets, etc., but they are so simple that we often do not pay much attention to these aspects. But once we try to understand things like spin liquids, which are not that complicated but somewhat different ideas, these basic features become quite useful. Okay, but these are nothing but quantum mechanics 101. Okay, so that's the structure of the. That's anything that I don't say. Okay, so that's about the degree of freedom. Okay, And Arun mostly dealt with this Hilbert space, okay, and pointed out how different normal spaces can arise in such situation. I'll deal with this Hilbert space, so I have a lesser complicated problem. Okay, so I'll point out how this works out. Okay. So moving on to the second thing, questions. Just feel free. Online people also, just feel free to stop me. I think it would be good if we have interactions. So the next thing is symmetries. In particular, I'll talk about what are called global symmetries. Again, these days with the latest developments, it's very important to distinguish between global symmetries because we have new things which seems to be important, like subsystem symmetries, etc., which I'm not going to. Okay, so I'll try to point out what I mean by global symmetries. So typically these things are of two kinds. Okay, internal and spatial or external or spatial. By the way, I'll strongly encourage particularly students if you want to come forward because as you have already seen that I don't have the best of the handwritings. Okay, so so it's, I mean, not always, but it's easy, useful to start with these two rough distinctions. This internal symmetry basically means that, as I said, that I have degrees of freedom at different points on the lattice or on a network. The internal symmetries basically acts on states at the same Hilbert space. So takes it to some U of I, there is some parameter. It does not change the particular Hilbert space. Okay. Example of this are spin rotation, time reversal, etc. Okay. So they don't change the position of the spin. Okay. Or the degree of freedom. Or in other words, they don't mix the local Hilbert spaces. Okay. Then there are external spatial symmetries, which basically changes. So under these symmetries, the I labeling remains invariant under internal symmetries. But for external symmetries, I goes to some R of I, say for lattice translation, the vector I goes to I plus whatever lattice translation. Okay. So it mixes, it sort of commutes the local Hilbert spaces, but of course the total remains same. Okay. So, okay. So basically what happens is that under these symmetries, psi I goes to psi of R. Typically, that's the these two acts. And examples of these are, say, lattice translation, reflections, etc., etc. Okay. So, and this, you see that this has this useful added feature that when it changes the, say, the state was here, and it by translation, I have changed it to say here. Okay, so the operator was acting on this Hilbert space, okay? Or the state belonged to this Hilbert space. Now it belongs to this Hilbert space. Okay, so often one says that the support of the state has changed. What one means is that the local Hilbert space is different, right? Just is this permutation. Okay. And for things like translation, the small translations, okay, which big translations can be generated out of the small translations, the untransformed state, the support of the untransformed state and the transformed state are close by. Okay, so if you do one translation, it was here, it's now here. But for all the states, okay. But for something like reflection, suppose I do reflection about this axis, okay, and there was this side here, okay, it gets reflected all the way here, so the support changes by big amount. Okay, so these are all structures that are already there in these.
If there is a translation and a rotation together, it will be an external.
Yeah, yeah. Okay, so anything which is of this form, okay. Again, you that's I soon make a statement that this is sort of somewhat artificial, but the example that you gave is of this kind. Okay. More questions? But this distinction gets blurred when we have things like spin-orbit coupling. So when we have L dot S, okay, it basically couples the real space with the spin space, and the symmetry that survives is often a combination of the transformations. Okay. So I think there was a talk on Kitay's model by Masafumi, who discussed some of its features. But let me just take, instead of going into the details of this, let me just give you an example in that case. Okay, so there were these honeycomb models where it had ZZ interactions on this bone, XX interactions, and YY interactions. Okay, so this, if you have this kind of, if you want to think about symmetries of these kind of systems, if you do spin rotation, it's not a symmetry. Okay, but if you do a 2 pi by 3 spin rotation about 111 axis, okay, followed by a lattice rotation, so those two together is a symmetry. Okay, so these kind of things, it's useful to start thinking in terms of them, but soon start thinking about how to destroy this structure, and that because we have examples and reasons to think about them in materials. Okay, so that's roughly the structure of the symmetry. But one important property is that, which is this global symmetry, that when you think about the transformation of the system, you think it in terms of product of unitary or anti-unitary transformations locally, and for internal symmetries in particular, and this value by which you are transforming is same at all points. You do the same, you rotate the spins by the same angle at every side, which is why. Okay. So this is the structure about symmetry. Question. Is this sound coming in because there are questions online? Okay. So, for questions. Okay. So the final aspect is this Hamiltonian, which we have And the Hamiltonian has this feature that it usually is a sum of few body terms. Okay, so the two body terms, you could write down one body term, etc. Okay, but this is the structure of the Hamiltonian, and the Hamiltonian where S all symmetries. So this is the structure of the Hamiltonian. This is the operator content, and this is the coupling constant. Okay. But one feature is that usually few body at a time and often local. Okay. And particularly the kind of things that. Okay. Questions. So the central realization, I think, of the last 50 years or more is that, I mean, of course, the realization was there, but more and more appreciated is that these three ingredients are actually effective, and their definition depends upon the energy scale of study. In the sense, if you're doing an experiment, okay, at some energy scale like 100 Kelvin or 0.1 Kelvin, okay, and you want to understand the phenomenon, you need to try and address these three questions at that scale. Yeah.
So in presence of spin orbit coupling,
Yeah.
so in presence of spin orbit coupling, the symmetry generators can be separated into the internal and external.
No, so it cannot be. So of course you can write down them separately, but often a combination of them is a symmetry that you want to consider. Okay, or more carefully, you would have to do a Klebsch-Gordon decomposition of both the symmetric groups corresponding to the external and internal, and some of the symmetries, which is a combination of the two symmetries, would survive. This. So when I have L dot S, this J is L plus S is the right thing, and I would like to consider the symmetries under rotation by J. Okay, that's one example. The example that I gave is another. But it's still useful to start thinking in terms of those two things. Yeah, more questions. Okay, so this is something that we would have to keep in mind, that these three ingredients, specifying these three ingredients depends upon the energy scale at which one is talking about, whether one is trying to do a theory calculation or one is trying to do an experiment, or even better, one is trying to do a calculation to explain a experimental phenomenology. Okay. This, of course, we know that at, say, the crystal formation scale, we typically have ions and electrons, okay, and they form the materials. Okay, if we go high, we do high energy scales. We don't even have ions and electrons. We have to think about subnuclear particles, etc. So we cannot formulate the problem in terms of ions. But of course, as conventional physicists, we don't do that. But once we go down, okay, the system crystallizes, etc. And particularly for things that are discussed, we think about the ions as roughly static and forming a crystalline background. And to understand the electronic phases, we want to think about electrons moving around. Okay, and there at some scale, roughly 1 electron volt, okay, we have these kind of effective description in terms of our models, where we have a kinetic energy for the electron, and then there is an electron-electron density interaction. Okay. Here the ions have completely dropped out from this description. And there is this four-dimensional Hilbert space, there are some symmetries, and I have this to be the Hamiltonian. Okay. But now, if I want to think about even lower energy physics for a particular system where there is one electron per site, okay, which is like the half filling, and I'm in the regime where T over Q is less than 1, okay, then as Arun might have discussed, that the electrons have a hard time in jumping around in the lattice, and we have this effective spin models where we have one electron sit per site, and then the spin can point up or down, and it can gain some delocalization energy by exchanging through spin exchange interactions. Okay, so those are basically less than EV. If one is thinking about d orbital systems, then this is typically of the order of hundreds of Kelvin, like 100, 200 energy scale. And if one is thinking about s electron systems, this is like 1 Kelvin or even less than that. So this is much below. So more carefully, this is much below the charge gap. Okay. So in that case, I already wrote down the Hilbert space. The Hamiltonian, which is what I'll now write down, is so this is for magnetic insulators. Hamiltonian for spin half. Okay, and then this is a spin exchange. Okay, and I can have four further, not only 2 spin exchange, but more spins interacting. I'll write down another Hamiltonian for this. And this typically has the form T square over U J. That's the second order perturbation theory that all of you must have done. Okay. So this is the generic form if one has spin orbit coupling. Okay. And this form can be written in a slightly better way, divide up these coupling constants, which is as follows. The bilinear terms. So this is the good old Heisenberg term. This is the Dyloshinsky-Moria term. And this is called the pseudo-dipole term. Okay? When you write down this generic form, typically it's useful to divide it up in this way. And this is the one that survives in spin rotation invariant case. All of them go to 0 because they break spin rotation symmetry, but may be allowed if spin orbit coupling is present and some others may survive, don't survive. Okay. Like for this term to survive, you need to have break inversion symmetry and things like that. One can do a symmetry analysis and get this form, and all these coupling constants are again T square over Q. Okay, so that basically is the 0th order problem that we know the structure of our Hamiltonian at say 100 Kelvin. Okay. And the experiments are done somewhere below 1 Kelvin. We would like to know the structure at that scale so that we can explain experiments. Okay. So how should we do that? Questions? Yeah.
The last two terms are coming from pyramid cupping, right?
Yeah, yeah. So these would come.
There is no possibility. Or pyramid cupping, you can
Yeah.
find.
You have to break spin rotation symmetry, as you can see that both these terms break spin rotation symmetry. More questions? Is there questions from online?
I don't think so.
Okay, so I'll think about these class of spin models. I'll add more terms, etc. But it would always be in terms of spins. Okay. So how do we proceed? Okay. Typically a very complicated problem, particularly when there are interactions, and we need classifying principles. And mean field theory tries to employ these classifying principles at an approximate level. Okay, so that it tells us how should we think about this problem of given a quantum system at some energy scale, how to think about the properties of the system at a different energy scale. Okay, typically a lower energy scale. Okay. And so then we need to know the classifying principles that we are up against. Okay, so that we can incorporate them in our mean field theory. Okay, and it seems that typically there are two major classifying principles that we have come across in condensed matter. So you have a system at say high energy, which are described by the spin Hamiltonians. I'll just keep on writing in the form. Okay. And you take this system, and if you're an experimentalist, you take the system at room temperature and cool it down. Okay. So temperature decreases. So you cool it down. And you're asking questions here. So the thing that they absolutely have to do, or almost always have to do, is to, as you cool down the system, is according to the third law of thermodynamics, they have to release entropy. So limit T going to 0, limit N going to infinity, the entropy per psi. So as you cool down the system, they have to get rid of the thermal entropy. And if one asks, how does the system choose to do it? That is a good way to formulate and try to understand the problem. Okay. Typically, there are two ways that we understand right now. One is the way that we are more familiar with, which is symmetry breaking. The state, the low energy state, chooses to break some symmetry and thereby get rid of the thermal entropy. Okay, this is the basis, and this we incorporate in Curie-wise type of mean field theories when we do calculations. Okay. The other and is, I guess that's the word modern in the modern field, mean field theory, is superpose and entangle. So these are two extremes. There are, of course, things in the middle where the entanglement properties and the symmetries interplay, and other people, Masaki, played an important role in discovering some of these things and pointing out some of these things pretty early. But these are the two extreme ways to get rid of the trouble. And this symmetry breaking way gives us states in the thermodynamic limit, which are almost product states, or they're very well captured by product states. This is the reason why this wave function very well describes an antiferromagnet, even though this is not an eigenstate at any finite n. Okay? And this is the reason why one can draw pictures of this kind. Okay, so this type of ferromagnet, antiferromagnet or a ferromagnet, and like this, because it's almost product state, so one can describe the system locally. Okay, and this local picture is characterized by this local order parameter, which we then put it to the mean field theory. Okay, but this kind of picture is largely missing on this side. Okay, one has to draw more subtle pictures to capture the fact that there are a lot of superpositions, and I think that some of these RGB type of pictures may have been shown, which you see that there are lots of states. I'll show more. It's basically completely different from these class of pictures that we can even draw, come across at high school when we think about bar magnets, pictures, notebooks, which are like class of versions. But this strategy won't work to understand this other class of phases which do not break any symmetries. Okay? Or symmetry breaking is not the primary characterization. Okay, so so we have to incorporate the. If we want to understand this, we have to incorporate this classifying feature in some crude way to form the mean field theory, and then start thinking about it more carefully. Okay, so that's the plan. And questions?
So which method to choose depends on the problem I'm looking at, right?
Yeah, of course. Okay. So that's often dictated by the experimental terminology and sometimes numerical calculations at various approximate times.
And the superposition entanglement kind of thing can be also done the mean field framework.
Yeah, that's what we try to indicate how to how mean field theory can form the first step of understanding this. But what kind of mean? Other questions? Yes.
When we are taking different terms in the Hamiltonian,
Yeah.
does it depend on the energy scale in which terms are to be taken? Like the Heisenberg interaction is there, that the DM interaction is there. The other interactions, as you said, we can add more terms to it. So how do we decide? Does it depend on the energy scale?
So, the question has twofold answers. The first step is that if I write down some terms, say OI, OJ, OK, okay, three operators, and take coupling constant like this, okay, and if this commutes with whatever symmetry I have in the system, okay, then it is allowed in the Hamiltonian. Okay, so that's a statement about the operator content. Okay. Now, there is another question thing that this is with coupling constant. Okay? So symmetry does not tell us what is the value of that coupling constant. Okay, I need a higher energy theory to determine what is the value of that coupling constant. For example, in case of the spin model, I just very vaguely indicated that J, in terms of the Hubbard parameters, J is of the order of T square over T. Okay. So what I did is that I had this high energy theory. I integrated out high energy degrees of freedom to arrive at this low energy theory. And then the parameters of the high energy theory dictates the coupling constants of the low energy theory. Okay. So this is why we would need a higher energy calculation of a first principle calculation or something like that, a quantum chemistry calculation to try to make an estimate of these parameters. Or we need a degenerate perturbation theory calculation. For example, if I think about doing a degenerate perturbation theory, starting with the Hubbard model to higher orders. Okay. So then I'll at second order I'll get at this order I'll get S alpha S beta type of terms. Okay. At higher orders like T to the power 4 by Q cube. Okay. I may start getting S. A S delta L. Or if I don't have time reversal symmetry, I might start getting 3 spin terms. Okay, so there I have to ask the question: if I knew the parameters of the Hubbard model, how big is this compared to this? Okay. Similarly, if I had an estimate from an ab initio calculation about these numbers, I am in a position to ask which one dominates. Okay, so that's the role of the high energy theory. It sets the parameters of the coupling constants of the low energy theory, and then their effect needs to be considered within renormalization group. So this is again statement of renormalization group that the high energy theory sets the coupling constants of the low energy. Okay.
What's the energy scale of diameter?
So okay, so it's all of this order. So okay, questions. So as I said that the DM interactions happen when there is spin orbit coupling. So to ask understand the answer to your question, we need to ask what happens to the Hubbard model in presence of spin orbit coupling. Okay, so in absence of spin orbit coupling, the U term remains as it is. Okay, so the on-site term remains this. Okay, the density term, it doesn't change. But suppose I have J equal to half instead of S equal to half. Okay, so then this term becomes sigma sigma prime Ij Ci sigma dagger Cj sigma prime. Okay, so this allows both spin dependent and spin independent hoppings. Okay, now for spin half, the J equal to half. Okay, this is a 2 by 2 matrix as a function of sigma and sigma prime. Okay, so as we know that any 2 by 2 matrix can be written as follows. So T sigma sigma prime Ij is equal to T naught Ij into delta sigma sigma prime plus I T Ij sigma sigma. I've just written a 2 by 2 matrix. So this denotes spin independent hopping. This denotes spin dependent hopping. Okay. So let me write this in a component way. Alpha. Okay. So now I can do a second order hopping process within for this second order perturbation theory, starting with this Hubbard model. Okay. So at second order, it is okay to consider 2 sides. Okay. So at half filling, so I start with 2 electrons, one at the 2 sides. Okay. I think about hopping this and coming back. That the intermediate step would cost an energy U. Okay, that's why this 1 over. Okay. But now I have many ways to hop, many amplitudes to hop. I actually have 4 amplitudes to hop, 1 here and 3 here. Okay, one of them is spin independent and 3 are spin dependent. Okay, so if now I can think about various hopping processes. I can think about going from here with a spin independent process and coming back with a spin independent process. That would give me T naught square over Q. That would be present even if there is spin orbit coupling is not there. Okay, so this is the coefficient that dictates the Heisenberg term. On the other hand, I can go from this and come back with a spin dependent hopping, provided symmetries work out correctly. Then I could have a term T naught into T alpha. Note that this is now a vector. Okay, this is what dictates this dilution Pimoian vector SI cross S. Roughly, of course, I have to implement symmetries to find out whether this term survives or not. But roughly, when it survives, it's of this form. And finally, the pseudo dipolar term I wrote is basically going this beta going this. Those are the 3 classes of terms. More questions? It's like 10:45.
10:45, yes.
10:45. Okay. But just keep on asking questions. Okay. So, as I said that I have these spin models, and I want to understand what the fate of these systems are at lower temperatures, and there are these 2 ways. Typically, this first way is what we are very familiar with, and this happens when we take such spin systems on biquadrite lattices. Like square lattice, this is the simplest example. We are all taught that we have nearest neighbor antiferromagnetic Hamiltonian on a square lattice, and even for spin half, this seems to go into a symmetry broken phase, the snail phase at low temperatures. Okay. So what happens is that the susceptibility, so in experiments, the susceptibility, if you plot so at high temperature susceptibility goes as 1 over T minus T theta. Okay, so if you plot the Fourier susceptibility inverse of chi as a function of T in experiments, at high temperatures, it follows this 1 over T with this intercept, and roughly when you reach this T theta scale, it starts deviating, and that's the onset of correlations. This is what nicely behaved magnets do. Okay, and this onset of correlation is related to the quenching of the entropy, the thermal entropy, by symmetry breaking. And this is what we usually capture by Fourier type of mean field theories, where we try to write down the SIs as average value of SI plus so this is delta SI, and this is the order parameter. So I put that in this Hamiltonian for and throw away all terms which are of the order of del SI del S square. Okay. So that's the Curie-Weiss mean field theory that we have all learned. Okay. We do this for antiferromagnet. We choose Mi is equal to -1 to the power Ix plus Iy M. Okay. Or is a Neal vector, we call it N. If we choose this pattern, throw away everything of the order square, should recover all the Curie-Weiss field theory results. But let's try to understand what we did. We sort of put the guess, okay, this information about possible symmetry breaking, and then we are doing the calculation. So the mean field theory is like trying to anticipate what the system is doing, and then trying to develop a consistent framework to describe that. Okay, one can ask, why did I choose this? It's because for the system I knew the answer, of course, but generically one would have to try and think about all kinds of order parameters and try to see which one wins energetically, which one is most best. Okay, one can make this more sophisticated. Again, I think Bhattacharjee has thought about these a lot more, but this is roughly the way to go. Okay, so you can think about all kinds of, for every symmetry, you can think about a way to break it, and think about that order parameter and try to do a mean field theory exactly like this. Okay, and you would get a result. You would get a mean field energy and things like that. Then you compare between different mean field energies, which one wins, add fluctuations. I'll add fluctuations to this. And this is typically how mean field theory goes for symmetry broken systems. Self-consistent mean field theory. Okay. I haven't added fluctuations yet. I'll point out. Okay. Questions about this? That how do we go about doing our Curie-Weiss mean field theory for symmetry broken systems? Okay. So then once we have this theory, what we do is think about long wavelength fluctuations of this order parameter, low energy fluctuations. So we write Mi as some M naught M naught I plus delta M R. So these are the long wavelength fluctuations. In case of magnetism, these are the spin waves. Okay. So these fluctuations describe the slow variation of the effective order of the order parameter, and in this case, these are the spin waves. Okay. And for antiferromagnet, this has a spectrum which goes at long wavelengths as T. And for ferromagnet, so this is for antiferromagnet. This is for ferromagnet goes at K square, and so that's like adding one more step to the mean field theory, symmetry broken mean field theory. Okay. So this is how one works and goes to the mean field plus fluctuations, low energy fluctuations. So what are the, so then the question has been formulated is that at the scale where I have, at low energy scales where I have only spin waves, what is the structure of the physics? Okay. The degrees of freedom are not these individual spins anymore, but these spin waves, which have this, in terms of the spins, which have this structure. They're block waves. let me write it for a ferromagnetic spin wave so that all up. This is like the ith spin take down. Okay, so you take the ith spin down and propagate it, superpose it at momentum k. Okay. That's how you get the block waves of spin waves, block states of the spin waves. Okay, and those are the degrees of freedom at low energy. Okay. If I want to calculate the quantum numbers, of course, the complete spin rotation symmetry is not there because the magnet is ordered, but rotations about the axis is now a good quantum number, and one can ask what is the quantum number. Say, if it orders along the z direction, one can ask what is the sz quantum number of this, and with respect to the ground state, and that delta, since I have flipped one spin, the delta sz with respect to ground state is 1. This is why we keep on saying that the spin waves of the magnons are spin 1 excitations. Okay. So when so this is basically the description, and I have to write down Hamiltonian in terms of magnons or the spin waves, which are bosons, and the low energy effective Hamiltonian is something like this: omega k, k dagger, where AK are bosonic operators which creates magnons. So you see that now I have the answer to this question, that at low temperatures, what are the degrees of freedom, what are the symmetries, and what is the Hamiltonian in terms of the spin waves. Okay. And how does it help us in experiments? Is that, for example, if you do a specific heat calculation, you basically calculate. It depends upon this dispersion. Okay, so you get a specific heat, which is, so if this coefficient is alpha, I think you get D by alpha. Okay, and you can measure this in thermodynamic experiments on the magnet at low temperatures. Okay. Or you can do something more sophisticated. You can go and do a neutron scattering experiment. And since the neutron is a spin half object, okay, what happens is that it goes with some omega I. So this is neutron ki and some spin, okay, si, and goes with kf, omega f, and sz. Okay. The initial final, and this may get transformed into a magnon. Okay, this delta s z can be 0 or plus minus 1. Okay, the delta z is the difference between the final and the initial spin of the neutron. Okay, so if it is 0, that's an elastic scattering. Okay, and if it is plus or minus 1, that's an elastic scattering with the magnon, transfers some energies and flips a spin, etc., etc. Okay, and when it transfers energy to the magnon, the initial and the final momentums and the frequencies of the neutron change, which is absorbed or emitted by the magnon. Okay, and that's how we can get an estimate of what omega of k in neutron scattering. That's how we measure magnets. And because it's a single particle, we have fantastic resolutions with the present technology. Okay. So we can see magnons on this. There are, of course, other experiments, topological magnons, etc. All these make sense because of this underlying feature that there is a symmetry breaking, and we are thinking about these things which are a consequence of the symmetry breaking. In fact, the fact that the magnons are gapless is because one is breaking a continuous symmetry, which is a consequence of a Goldstone here. Okay, the Nambu-Goldstone bosons. Okay, so basically starting with this mean field theory, one can build up the entire understanding of the low energy theory if the mean field theory is correct, if the starting point is correct, where the classifying principle, in this case, the right broken symmetry, is incorporated. Okay, if one incorporates a wrong symmetry breaking, then like completely wrong results. One has to sort of throw away that. But if one implements the right symmetry breaking, that provides a good starting point. Okay. So the question then is that how do we go about this kind of structure when we do not have symmetry breaking? Okay. And in other words, this thing that I very vaguely pointed out, this idea of entanglement, etc. Okay, how do we incorporate them? Questions? Oh. So I have like 10 minutes, maybe. That's okay. So the plan is as follows. Can we get rid of this? The plan is as follows. I'll show you an example of which are the classifying features that we need to incorporate for an exact model. Okay. This would be sort of similar to the honeycomb model that was Masafumi discussed. Slightly simpler generalization of that. The Cody-Short model, maybe most of you have seen this, but I'll go through this, trying to point out the central features that we need to capture. And when we come back after lunch, I'll tell you exact and an inexact way to capture that generally, which would be like doing mean field theory without breaking symmetry. Okay, so I don't know. So I think that one of the things historically may not be the first. I don't know that. Unfortunately, I don't know the history that well of this feature. But one of the first attempts to sort of forcefully point out that doing mean field theory is possible without breaking symmetries was this paper by Phil Anderson, Bhaskaran, and other people who pointed out the relevance of these mean field theories. Okay, so to do exact calculations and to compare energies with these mean field theories without breaking symmetry may not be the right thing to do, particularly as we understand now. But they provide us a useful way to get to the low energy theories without breaking symmetries, and we end up with a different set of degrees of freedom, etc. And this is the thing that we would need to try and understand. Okay. So, has this story code been discussed before? Sorry, extremely sorry, I couldn't attend much of this.
No.
Okay. So let me try to point out in the next 10-15 minutes this, I hope, a simpler model to what Masafumi discussed, which only requires us to sort of diagonalize 2 by 2 matrices, the following matrices, but it would convey the central features that we would absolutely need to capture when we want to develop a mean field theory for a spinning. Okay, so the particular model, and so this Hamiltonian would look very artificial, and it is, as far as we understand, I mean, it's not very artificial, but it's somewhat different from the Hamiltonian that I just wrote down. But the advantage is that it is exactly solvable, whereas the Hamiltonians that I wrote down are mostly not solvable exactly. And you know that many body exact solutions often convey a wealth of information, and this is what we are after. Okay? I'll sort of guide you through the particular set of information that we would need to be careful about. Okay, so this Hamiltonian is of the following form. There are various ways of drawing this, and this is because of, again, Kitaev, who pointed out in late 90s, I think, this Hamiltonian, and this is of the following form. So I do a square lattice, but unlike now, I choose to put the space on the bonds. Okay, So these black dots are where the spin halves are sitting on the bonds. Okay. And this is the particular very fine-tuned Hamiltonian. It has two terms. One with coupling constant Jx, which is basically of this form that you think about one side, there are 4 bonds coming out of these sides. Okay? You think about the 4 spins sitting on this bond and take a product of their x, sigma x components. Okay? So sigma x, sigma x, sigma x, sigma x. Okay? And then you do it at all sides. You do it at this side, these 4 spins, take that sigma x component and put that product. Instead of 2 spin, it's a 4 spin term. Okay? So this is okay. It's fine for this term. So this term is this yellow thing that you now don't think about the side, but the placket, the center of the placket, okay, like this. And it has 4 sides. Okay, you take the 4 spins and take the sigma z component and take their product. Okay, earlier you took the sigma x component and took their product for the sides, but for the plackets, you take the sigma z component. So for this placket, sigma z, sigma z, sigma z, sigma z. Okay. For this placket, sigma z, sigma z, sigma z, sigma z. That's this second term. Okay. Yeah.
Is there a reason to choose why yes choosing the Z component for the plackets and X for the?
You can flip them, but this particular form 1x and 1z ensures their exact solvability. Okay, it's but this. So most of what I say basically is a particular feature of this Hamiltonian. Okay, so so the Hamiltonian is clear, then most of the statements that I say would be like trivial, but the Hamiltonian is sort of non-trivial, and this non-trivial arrangement is to make it solvable so that the central features become like very clear. And we'll carry those central features to approximate Hamiltonians. Yes.
So when we've been looking at the symmetry broken states,
Yeah.
So that was to say like explain magnetic systems.
Hmm.
So in this case, like what is the kind of motivation?
Okay, I don't know what your definition of magnetic system is. Anything which only is described by the spin degrees of freedom is a magnetic system for me. Okay, magnetic insulated
Right.
physics.
So
Okay.
most like what are the systems that will not break symmetry and like there are like spin liquids or something
Yeah,
like
yeah.
that?
So I'll come to that. This is an example of spin liquid. So let me first discuss a concrete example and then come to approximate statements. Okay. So that's otherwise we can follow that through too, but we'll need a semester. Okay. Yeah. Okay. So this is a Hamiltonian. So if we take this Hamiltonian, okay, and think about these different AS and BP operators, note that they're product of this sigma matrices. So they're square, sigma matrices squares to identity. So they're squares and identity. Okay. So also they're Hermitian operators. So that means that their eigenvalues are plus minus 1. Okay. So both AS and BP have eigenvalues which are plus minus 1. Okay. And then this is crucial that if you take the different AS operators and the BP operators and AS as well as the BP operators, all of them commute with each other. Okay. This is particular to this structure. I mean, the fact that the AS operators commute with each other is like no brainer because they want sigma x always okay. The same for BP. But this is more tricky, slightly more tricky, in the sense that if I choose this placket and this side, they don't share a common spin, so it's clear that they come in. But suppose I choose this placket, this side, and the placket next to it. Okay, so then they share these two sides, and we have to be careful. Okay. But we know that sigma x and sigma z anti-commutes. Okay. And there are two such things. Okay. This anti-commutes, the sigma z and sigma x here anti-commutes, the sigma z here and sigma x anti-commutes here. So two anti-commutation leads to the fact that the A operator and the B operator on adjoining placates sides also commute. Okay, it's just this. And so this is true for arbitrary settings. So what we have is basically an infinite set of conserved quantities or order n set of conserved quantities, which makes this problem exactly solved. Okay? That's it. Okay. So then, if it is exactly solvable, we should know the ground state, and this is where the surprise comes. Okay. Here we see. So, what is the ground state for the system? So let's try to construct the ground state again in an open system. Okay. And so let's start with a state which is where all the sigma z's are pointing up. Okay, so that's so what we want in a ground state is basically the ground state with all the AS operators. Their eigenvalues are +1 or -1. We want the +1 and BP to be -1 because this being the Hamiltonian. Okay, if these operators are the eigenvalues are +1, then this has the minimum energy. Okay, with the AS and the C being assumed to be positive. Okay, so we want that property of a ground state. Okay, so let's try to construct that. So let's start with this state where all the spins in all the bonds are pointing up. Okay, that clearly satisfies this condition that the BP acting on any side, all the sigma z's are up. So the product of sigma z is also +1. Okay. So they satisfy this. But let's try to check this. Okay. So you act with AS on this state. Okay. What happens is that if AS is on this side, it basically flips only these 4 spins. Okay. The rest it doesn't touch. But now, if I try to calculate the BP of this state, okay, this is plus, minus, minus. So the product is still plus. So AS acting on this all up state, okay, gives a state which still satisfies this constraint. So it satisfies all the BPs. So then I can act with AS here, everywhere, and get a state which still obeys this constraint. Okay. But now what happens is that if I act with A, suppose I take this state and act it with AS. Okay. It basically annihilates this, turns this back, and takes me back to this state. So the thing that the AS operators does is that they flip spins in a closed loop. Okay, if I think about a product of AS operators here and here, they would flip a set of spins in this bigger closed loop. And acting with further operators sort of permutes between different states with different closed loops. Okay. And that's essentially what this thing is. What it is basically you take the all up state, you take one loop of down state, you take a bigger loop, you take 2 loops, and take equal superposition. Okay, if I expand this. And once you do this, clearly this satisfies this BP to be +1. But once we act with AS, okay, they just permute between different states. Okay. So the ground state, unlike in the ferromagnetic case, is not this almost, or antiferromagnetic case, almost this product state with some swings pointing up, some swings pointing down, and some swings pointing down. Okay, but this superposition of state with closed spins on closed loops being down in a background of up spins, and it's like a huge superposition. So if you go and calculate the expectation value of one spin, okay, it has equal probability of sitting on the loop or not sitting on the loop. So the average value is 0. Okay, so the expectation value of all local operators using this ground state and all the low energy states are zeros. So there is no symmetry breaking or no correlations that develops. Okay. On the other hand, it has so the ground state does not break any symmetry. Okay. So let me actually stop here because without going into the excitations, once we come back, so let's take questions about the ground state. Once we come back, we will deal with excitations and we'll find that the excitations are also not of the form of speed waves. And then we will move on to try and understand how to describe them. Okay? Okay, but questions about this ground state?
Thank you very much.
So the reason that there is no local order parameter is the degeneracy. Highly degenerate states are present.
There is no degeneracy. This is ground state. Okay? There is no degeneracy. This is very important. Okay, so third law of thermodynamics forbids degeneracies for quantum systems at zero temperature.
So the states with no loops and states with loops, they are different. So what are the energy? They are not energy eigenstates.
No, they are. This is the energy eigenstate.
Yeah, but individual states,
They are not eigenstates. Okay, this particular superposition. If you change the coefficients, this is no longer a eigenstate. The state that you are talking about is 1, 0, 0, 0, 0. That's not an eigenstate. Okay.
Okay.
So this particular superposition is the eigenstate with the lowest energy and an open system. Okay, one can construct other ground states on a torus, etc. But this is an explicitly constructed ground state. There is no degeneracy. So the degeneracy would lead to zero temperature entropy. The entropy has been quenched. The thermal entropy has been quenched. Okay, by superposing.
So there is no symmetry breaking is happening here.
So no symmetry breaking, but quenching of entropy, thermal entropy.
So like topological phase transitions, where there also no symmetry breaking happens. So what is the difference from this point of view?
You have to wait till lunch. Okay, we'll see what are the problems. But it's closely connected.
Any other questions? Okay, so breakfast, Professor. Okay. We will start next. Oh, from 11:15. Yes. Take away.